Hello all and welcome to an exciting video lecture in engineering mathematics brought to you by your instructor Srinidhi from the Bharadwaj Academy. We are in the first module of differential calculus of part 1 of my 4-part series of lectures on engineering mathematics. Today we'll be discussing about the Taylor and the Maclaurin series, which is a very important series that we'll be constantly visiting in the higher engineering concepts. So are you ready? Yes, so I'm ready. Before we understand the Taylor and the Maclaurin series, we need to understand its origin. So the Taylor series originates from the concept of Taylor's generalized mean value theorem. So this theorem serves as a general theorem from which other mean value theorems can be derived, which we'll be seeing very soon. It goes something like this. So basically, it means that the function is continuous in this interval and differential up to the nth order. And there exists a number theta such that, yes, so as you can see, it's a very long expression, but we need to concentrate on one very important term, which we call as the remainder. Yeah. Now, can you see that there is a term a plus theta h here? What is the meaning of this? So let us focus on the very nature of this number a plus theta h. So let me tell you that this number theta lies between 0 and 1. Now let us take a here and we'll take a plus h here. So as you can see, a plus h is a number which is greater than a, and the difference between the two of them is, of course, h. We'll call this the source and we'll call this the destination. Theta cannot be more than 1, which means that a plus theta h is such a number that is lesser than a plus h but greater than a. So it can be here, it can be somewhere here, or it can be somewhere here. Now, how is this actually relevant? Let us see this with the application of this generalized theorem to the Lagrange's mean value theorem to understand the same. Now, how do you obtain the Lagrange's theorem? It is done by putting n is equal to 1 in the Taylor's theorem. So let us understand more about this. But first, if we put n is equal to 1, we get this expression. Yes. So what does this mean graphically? Check out this graph. Now, as I've already told you, A is here. Yes, let us call this point A, the starting point, and let us call this A plus H, which means this length is H. Now, A plus theta H is a value in between the curve, as I already have told you. Now, what about this number? Yes, it means that the differential of the curve f of x at this point, the differential of the curve at this point, yes, is equal to the slope of the tangent at this point. Now, does this RHS look similar to you? Yes, it does. You have y2 here, you have y1 here, and you have x2 here and x1 here. But you might say there's only h here, but can you see that a plus h minus a actually gives me h? So as you can see, you have x2, x1, and the f of a plus h and f of a are nothing but y2 minus y1, the points on the y-axis, and these are the points on the x-axis. So on the RHS, you have the slope. So this is what we can basically infer from the Lagrange's mean value theorem. Now, the slight variation of this can be seen in the Rolle's theorem, where it is completely flat. Yes, this happens when f of a plus h is equal to f of a. That means it is completely flat, which means let's see this. So this means that this point and this point are equal along the y-axis, and there should exist a value where the slope is 0, which means the tangent at this point is completely flat, which also means it is parallel to the x-axis. That's right. Now we'll understand how we can obtain the series using the Taylor's theorem. Here, as you can see, the order of differentiation n tends to infinity. So this f of a plus h becomes a sum of infinite terms. Now, in this, if a is equal to 0 and h is equal to x, we obtain the Maclaurin series, something like this. Now, if a is equal to x and h is equal to x minus a, we obtain the Taylor series. As you can see here, any function can be f of x can be expressed as a sum of infinite terms in this way. Now let us understand this in a more graphical way. Take a look at this function f of x. Now let us take a point a. And as you can guess, this is f of a. Now here, what is f dash of a? Yes, it is a straight line, the tangent to this point here. Basically, the slope of the tangent drawn at this particular point. Yes. Now, let us draw f double dash of a. What is f double dash of a? It is the slope of the tangent to the path traced by the tangent of the original curve. Yes, so you get something like this. Now differentiate it again and again. This is f triple dash. Yes, this is f 4 times. Now, can you make a small observation here? That every time with successive differentiation, it is brushing along the point slightly by joining with the original curve. So imagine this. You are doing it a number of times, basically infinite times, and add it all of them. Yes, you guessed it right. You get the original function f of x. This is what is conveyed in the Taylor and the Maclaurin series. The difference between the two of them is just that if a this point is equal to 0, it is becomes Maclaurin series, else it is Taylor series. So as you can see, Maclaurin series is a special case of Taylor series. Let us try to express a very simple function which we use in math daily in the Maclaurin and the Taylor series. Yes, so let's take f of x as sin x, a very simple function. So here is a list of the derivatives up to the fourth order. I think this is simple, right? Derivative of sin x is cos x. You differentiate cos x, you get minus sin x, minus cos x and sin x. Now first let us see Maclaurin series. For that, you have to take a is equal to 0 and f of a is, yes, sine 0 is 0 and f dash of 0. So substitute 0 here, we get 1 and f double dash of 0. Substitute here minus 0, it's again 0 and f triple dash of 0. Substitute 0 here, cos 0 is 1. So we get minus 1 here and f4 times of 0, yes, you again get 0. Now, once you substitute all of this, you get this. I want you to try it yourself. Yes, this is the expansion of sin x in Maclaurin series. Now, for Taylor series expansion, you need to take a value for a. So let us go with a is equal to pi by 2 or 90 degrees. The process remains the same. Let us find these function values at pi by 2. So what do you get? We all know what is f of pi by 2. Yes, f of pi by 2 is sine pi by 2 is just 1. Now, if you substitute here pi by 2, we get 0, and here again it is minus 1. Here it is 0, and here it is 1. As you can see, it is slightly inverted from what we did in Maclaurin series. So on substituting, we get this. Now, if you observe, in the Maclaurin series, we had odd terms 1, 3, 5, and 7 with alternating minus and plus. And here we have 0, 2, 4, 6, the even terms with an alternating minus and plus with a basic difference. So this is the Taylor series expansion. Now, why don't you all try the Taylor series expansion at A is equal to pi by 3 and let me know in comments if you are able to obtain the results. Try it. Here is a list of Maclaurin series expansion of some important functions such as e power x, sin x, which we have already done today, cos x, and 1 by 1 minus x. Now, this is a very strange function that we are taking as a important function. Why is that? Observe the expansion here. Can you see that all these terms are in a geometric progression with a is equal to 1, the starting term is 1, and the common ratio, the number which you have to multiply to the successive terms, right? This common ratio r is x. So this RHS in this particular example is sum of infinite terms that are in a GP with a is this and r as that. So if you take 1 minus 1 by x, put this as a and put this as r. So we get a very important result from the Maclaurin series expansion of this function, that the sum of infinite terms of a geometric progression is a by 1 minus r. This is very, very helpful in many engineering applications. Thank you for watching this video. Please make sure to like this video and subscribe to my channel. Also, leave in the comment section on any suggestions, feedback, shortcomings. Stay safe. Bye.